Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about space weather. So let's dive right into it. Well, first we have to understand what we are talking about. We are talking about events that affect space around Earth. This is a very critical aspect. We are not looking at a whole solar system nor whole Milky Way, only a sphere around Sun. Now, how big is the sphere? Well, that depends how far your satellite is. Basically, that's the whole point. That's why we care about this whole system. So basically, think of it this way: take a geostationary orbit, make a sphere around that, something like that. That's our primary focus. Now, there are other things in the Milky Way, other things in the whole universe that affects our space weather, even in that sphere. But all of their effect is amount to almost zero compared to Sun. So that's why most of the time we are only focusing on Sun, because yes, there are other sources of cosmic background radiation, cosmic rays, and all that jazz, but all of them are amounting to almost nothing. So fundamentally, we only focus on Sun. So particles coming from the sun are the primary factor here. Now this may sound odd, it's like sun is a very huge thing, which means it has insane amount of gravity. How the heck something is leaving that? Well, because it's a reactor, it's literally going boom all the time. It has enough high energy particles that can literally leave the surface even with insanely high gravity, and not to mention it has magnetic field to push them, it has photon pressure to push them, it has enough there to actually do this. And there is a constant amount of gases leaving basically sun surface constantly, like there is a minor wind coming out of it. However, be mindful, by the time it reaches Earth's diameter, basically Earth's orbital diameter, 8 light minutes is almost diluted to vacuum level. So but overall it does have an effect, and sometimes a sun has a tendency to sneeze, which we call coronal mass ejection. At that point there is enough oomph coming out that you can detect it directly. So that's what we are talking about here. However, be mindful, while we are talking about space, it does have a direct effect on Earth. Another aspect is the reason we started to care so seriously about this is basically risk to our space infrastructure. We just don't have ISS there. We have GPS system, we have GLONASS system, we have Galileo system, we have hundreds of other things, and soon we'll have something like Starlink also. So those things are very precious and important to our day-to-day life for fundamental reasons. If something bad happens to all of them, we're gonna have daily like basically disruption of our daily life. It's not just like who cares. No, it's like you will know first thing in the morning that something bad happened in space, because it's that important. It's not just like a nice luxury. No, it's important. Now, one thing you have to understand, sun wind, while it's very diluted by the time it's reaching us, it still has enough oomph in that if Earth did not have a magnetic field, over time it will just erode the whole atmosphere, and it will start with light elements. Now, thankfully, Earth does have a magnetoshield. That's why we can protect our precious element like nitrogen, like oxygen, because if we did not have magnetic field, we'll still, because of our gravity, we'll still be able to hold an atmosphere. Example, Venus. While Venus is much closer to sun and is getting bombarded by even larger amount, it is still holding on to its atmosphere, but because it does not have magnetoshield, it cannot do anything about light elements. For example, nitrogen is like, peace, I'm out. Oxygen, peace, I'm out. So those things happen. You have to understand that aspect very seriously. Now, because there is a magnetic field and because sun is releasing charged particles, those have an interaction, and that interaction, if it sounds like almost interaction in a generator, yes, it is. It's just like oomph. A lot of basically quote unquote short circuit event kind of things happen when you have giant magnetic field interacting by giant wave of charged particle, and that causes electrical surges. Now that surges could be planet wide. Now if you're talking about 1900s or 1800s, you are talking about telegram wires going boom. If you are talking about something a bit early, you are talking about like Quebec's electrical grid going boom. And sometimes very recently you could have a scenario where whole basically Canada's grid went offline for a few minutes. So these sort of things have effect on our day-to-day life. It's not just like, oh, who cares? No, this is, you will know that kind of importance. So it does have that electrical surges. And because Earth's magnetic field protect us, it has a kind of unique property, as in like it's doing its job and we can see it's doing its job. How? Because charged particle, they are charged, they want to dump their charge, they want to reach a stable state, quote unquote. So what happens when you have magnetic field? All the fields are focused on North Pole and South Pole, and those where like once the particle hits, they stream in those locations, North Pole and South Pole, and we get aurora. So that's the whole point. That's why we get aurora. Auroras are like basically those particles interacting there, and they are giving off the energy, and we can see that glow after night glow. Now, because of the structure of Earth, basically Earth is there and it has magnetic field like that, it is creating quote unquote donut zone. Now those donut zone is a bad place for particles, because of the magnetic field they will be trapped there, and quote unquote we end up with our Van Allen radiation belt. Because particles are trapped there, they get like a idiotically charged particle are keep colliding on top of that. On top of that, once we already have a charged particle, you are getting bombarded by cosmic radiations. It will inherently over time start to reach a point where this whole zone will become idiotically radioactive. Like it will be more radioactive than anywhere else. And this puppy on Earth is like bad compared to Jupiter. Jupiter is like bonkersly bad, and it's really bad for satellites and humans. It's really, really bad. Like the best solution you have, A, to avoid it, B, to go through them as fast as you can. It's like in Apollo mission, they are like, they directly bypass the inner one, which is the more radioactive one, and the outer one, they are like as fast as they can do. So that's how we try to avoid that. And if you have to do long-term stay, for example International Space Station, you'll make sure it's below lower one also. It's like, no, I don't want to fight it, because even satellites that are designed to handle something this intense, they break down over time. It's like water eroding a stone. It's not going to happen overnight, but over time it's going to roast your satellite. So if you want to put your satellite for long-term use, you will put them either low Earth orbit, so it's protected from this, or you'll put them much outside of this, so it's like, getting much lower radiation doses. And if you have to go through this, yeah, you better have multiple spare satellites. And now you know why GPS have way too many spare satellites. So that's the whole thing you have to understand. That that donut trapping, that is really awkward for us to deal with. And because of our magnetic field, like, we cannot complain about that, because simply if we did not have that, we may look closer to Mars, or practically speaking, we may look closer to Venus. So that's what will happen on Earth, and that is big enough, important enough. But we have to understand about space as well, because those are much more vulnerable. On Earth we can manage it. It's like if something bad happens, we can manage it. We have some sort of robustness, but in space we don't have something like that. So you have to know, a large amount of charged particle, they can mess up anything. If you have large enough charged particle flow coming towards you, and coming from like basically a daddy like sun, yeah, bad things is gonna happen. And we have to understand, the older satellites we used to have in 1960s, most of them were analog satellites, and they were very robust electrically. They were very robust. They were not sensitive. They were not working on microvolts or things of that nature. However, once you start to make a semiconductor technology that is like 1000 nanometer, 500 nanometer, these things are ludicrously sensitive to these things. And that's why you will never see like the NASA is using like 10 nanometer processor on their Curiosity rover, simply because cosmic radiation itself will keep bit flipping it. It becomes much more vulnerable to those things. Now when you are talking about something directly has to stay in space permanently, the only way you can do shield against that, A, use bigger nodes, B, shield those puppy like there is no tomorrow. Now even with shielding, even with you utilizing much more quote unquote space grade hardware, over time it will still do damage. And the things that are more susceptible to damage are the things that we need inherently. For example, solar cells, they are exposed. You can't shield this puppy, you can't cover them with aluminum foil to alleviate some charges. You have to have these things exposed, and consequence, they will get damaged over time. So that's one thing. Another aspect, imaging sensors, basically like anything that is sensitive enough to detect anything else inherently becomes sensitive enough to detect all radiations also. So fundamentally think of this way, astronauts in ISS, once they close their eye, they start to see flashing lights, simply because of the radiation that is reacting with them, like cosmic rays. Now same thing will happen with Hubble telescope also. It's like once they are going through like those peak regions, they are like, okay, close the Hubble telescope, because if it has open shutter at that point in time, bye bye sensor. So fundamentally these things are inherently vulnerable, and we cannot do anything about it. It's like we have to just plan it properly. We have to use, it's like better to shut down the satellite rather than to risk roasting it. So it is something that is very seriously considered while we are designing the satellites. And those satellites which we were like for cost cutting reasons, or somebody did not talk this thoroughly, unprotected satellites, they became space jump because of that. So it has happened. We have lost satellites where satellites that were built properly, they're like good, they can handle it. Satellites that were built improperly, they died way too early. They were like, they're supposed to last 10 years, they died in 5 years. So you have to understand, even hardened the satellites are like designed to handle it, like built like a tank, they still also suffer from this, because again, you can't do anything to solar cells. So that's what we have to understand. This is something that we have to study. This is because if you have something like ISS, this is not small enough where you can just like, hey, let's turn it off. You have to avoid doing that no matter what happens. And this is big enough, serious enough, important enough, expensive enough that you have to study whatever effect happens on this. Now, how do we defend against it? Like, okay, we have an issue, we have vulnerabilities. How the heck we protect our vulnerability? We have line of defense here. Now, thankfully, while coronal mass ejection, while they happen, they are huge and they dump insane amount of particle towards our direction. Sometimes when sun is feeling a bit too generous, it does not travel at light speed. However, the event does generate enough of a pulse event where we can detect it using satellites, using basically observatory. We can detect the light flash that happens, and it happens in all spectrum. So we can detect like something happened. It's like on almost like a muzzle flash. We detect that puppy. Now that puppy we detect after 8 minutes of happening. Okay, we are already 8 minutes behind schedule. However, those smart ejection, but they are ludicrously powerful because they are directly taking energy from sun's magnetic field, which is like a mess. So it's almost like a rubber band going snapping. It's ludicrously powerful. It's happening from sun, but it's still not light speed. So it takes around 1 to 3 days on average. Sometimes it's really fast. It may reach us as like as early as like 15 hours. Now because we detect this puppy, the early warning system are issued the moment we detect it. The moment we detect the directionality, the moment we detect no, that Mars direction is gonna hit us, we are like, okay, early warning issued at that 8-minute mark. It's like once our satellites, once our observatory detect it, we analyze the direction, we got it. Okay, early warning is already issued. We are not gonna wait for the mass ejection to hit us. We are like, early warning issued. Like everybody's like observing everything they have to observe thoroughly. After that, we have like our quote unquote buoys in space. Now these things will get hit by the mass ejection. Now these things are basically as far away from Earth as we can put that, but it's still like, you know, few minutes away. Now benefit of this is once the moment they get affected, they'll tell you exactly what amount of energy is there. Because again, if you put a satellite that is very close to basically sun, you're gonna get over reading because of like, again, it's not diluted enough. But if you have just you know, basically in like low Earth orbit, you can't do much about it. It's like the mass ejection already hit it. So we try to put somewhere in between where it's like, you know, far enough where we can get early enough warning. For in this cases, around 15 minutes of early warning is possible at this point in time. So this gets affected. Now imagine worst case scenario, it was so powerful it get destroyed, emergency alert would be auto sent. It's like, bro, satellite gone, shut down everything, emergency, like done, shut it down. Do not try to assess the situation, just shut every power grid down, because you do not want to find out what happens if you don't. So fundamentally this is these two things, like basically we can see it and we can detect it, the light post basically, and because it's not traveling at light speed, we have response time. Now what happens, this puppy detects it and then we analyze what kind of intensity we are talking about. We already got it, we are already ready. Basically power grids were like, okay, shut down some generators, try to reduce the power cut, or you may already start to have power cuts at this point in time. Like grid station would be like, dude, if we have to you know, basically quote unquote isolate one generator for the supply, like worst case scenario, everything goes down, we still want to restart the grid, they have to have a one generator but is completely isolated, they have to disconnect it, so, or quote unquote turn it off. They would have started to do that at the moment we detected that. So once we detect what kind of oomph we are talking about, like what kind of energy is gonna actually hit us, we are like, okay, this patch, this area, because at this point in time we already have the directionality and we are also already traveling, already hit the buoy, we know what exactly is going to happen. Based on that, things will be taken care of. Basically at that point in time, grid will be like, okay, try to slow down the load, just have little bit so you can handle the surge. If nothing happens, awesome. A worst case scenario, you're gonna have some annoyed customer, and if you don't take it seriously and this puppy reacts like a red alert and you ignore that, yeah, bye bye your grid. So fundamentally this is our line of defense. A, we can see it, see the muzzle flash, and B, we detect the basically bullet traveling towards us, and that's how we protect ourselves. So this gives a very precise and accurate early warning system. That's why nobody knows about these things, because this is accurate. It's not just like a vague system. It's a very weirdly precise. It's like, this is gonna happen exactly at this point in time, at exactly this time, in the date, place, location, and like you can see the map where they're gonna say, like, okay, this spot will be hit by it, and please try to avoid going a plane around it. Like planes could be rerouted, grid could be preventatively shut down. These things happen like on a daily basis. Like again, the day when these things are happening enough, like nobody cares about it, simply because that's being done so efficiently. So that's why our line of defense, we have some shields in place to take care of our precious situation. So what we can expect in the future? Well, you have to understand, because of importance of our space assets and the fact that we are relying on more on aircrafts, more on drones, more on everything that relies space infrastructure, we are putting a lot more effort into space network. Like flat out, we have to understand the space weather fundamentally. So first tool in our arsenal is basically more space and ground based observatories. We are dotting the whole planet with observatories. The reason for that is, like, more data point you have, the more precise understanding of sun you have to get basically. And you have to know the sun is huge, as in idiotically huge. So because the sun is so huge, you cannot make one telescope that can study it whole. You can only make a telescope that, okay, either it makes it very low resolution where it's like, okay, it projects a sun to, let's say, 1 meter diameter. You're like, okay, 1 meter diameter, but you're shrinking something that is much bigger than Jupiter into 1 meter diameter. Yeah, you're gonna ignore most of the detail. Thankfully sun is very bright, so we don't have to worry about aperture. We just have have multiple basically systems focusing on a small area. So if there are multiple, if we have multiple observatory, we can observe multiple let's say dark spots on sun simultaneously. That's why we have to have multiple observatory. One observatory is not, it cannot look close enough because sun is huge. So fundamentally, that's why we are building more observatories and more space-based observatories. And the further we express them, basically space, quote unquote, space buoys around, basically space observatories, we'll have much more precise system. We'll have much better detection. And imagine this way: a solar flare hit or malfunction caused the satellite to like basically send out red alert. It's like satellite is down, do emergency shutdown. You would want to have some redundancy where it's like, do we actually need to shut down? Because again, you could cause a loss of life if shutdown happens in, without any serious reason. So that is something very thoroughly considered. Now again, these satellites are built like a tank, designed as a bunker, because again, it's supposed to get hit by coronal mass ejection. So it was built like the best way NASA can build it. But again, you still would want multiple satellites to confirm your response. So more and more is the key. Another aspect is, because we are gathering so much data at this point in time, we are starting to understand basically sun better, and that is the core key. That's the final end game. Think of it this way: before we understood tectonic plates, we knew earthquake was something that happened, something we couldn't measure. We did not understand why the heck it was happening. After we started understanding tectonic plates, it was like, oh, that's why it's happening. Oh, that's how it happens. That's how much energy it creates. That's how we can, early warning systems are now in place that can detect basically shock waves like as early as like 3 to 5 minutes early. So that's enough for basically bullet train to stop, apply emergency brakes. So the moment early shock waves are detected, it's like, okay, apply emergency brake before the major shock wave hits. So understanding is the key. Same happens on sun also. We are pouring as much money as we can do, building as many observatory in space, in earth, we can do, and we are studying the hell out of it so we can understand it thoroughly. Whereas like, okay, at this point in time, at this solar maximus is gonna go achu, and we're gonna be ready for that. Because if sun does very emotional achus, there is a very serious risk to us. So this was my presentation on space weather. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.